Fantastic. All right. Thank you very much for the introduction, and thank you especially to Michael for taking care of any of the zero and ultra low field detection questions, ideally. So I can focus a little bit more on the extra esoteric aspect of looking at new physics. This work has been done the Helmholtz-Institut in Mainz under section leader, Professor Dr. Dmitry Budker, and also some of the work is involved in this ZULF NMR innovative training network that is funded through the Marie Curie Axions. So I'm going to talk about, again, new physics and how parahydrogen gets involved in that. Apparently I am not able to click. Let's see if that helps. Okay, so we're taking sort of an interdisciplinary approach. Again, considering that, I once upon a time was I at least identified as a chemist, despite working in magnetic resonance, where really a lot of us are practically physicists a lot of the time. But I think operating in this sort of overlap between physics and chemistry is really useful because we are allowed to use the tools of physics to do a really good job of measuring chemistry. And actually, we can also use that to feed back and use chemistry to design and tune samples to give the best possible physics experiments. So if I'm going to be talking about new physics, I should identify what I'm talking about when I mean old physics. Probably everyone's familiar with sort of Newtonian dynamics. You're familiar with the fact that gravity works, you can only jump so high. And especially in the NMR world, we know about electricity and magnetism because that's pretty much what we do. And also, of course, chemistry basically is just, somewhat less familiar probably is the weak nuclear force that drives radioactive decay and other effects. One of the hardest forces to understand is the strong nuclear force. We can do pretty well at high energies where you have colliders, but if we're talking about low energy, I don't know if anybody saw Ilya Kuparov's talk about the origin of spin on one of these Zuminars. But again, whereas we know where spin comes from in terms of symmetry, we can't even effectively predict the magnetic moment of a proton. So everything gets really, really hard in terms of understanding what's going on there. But again, we know the basics of how it works. It's just that the calculations are nigh impossible. More recently, we had, for example, the confirmation and discovery of the Higgs boson, and even more recently, measurement of gravitational waves from binary black hole mergers. So, we're getting a better and better sense of how our universe works. That said, there are still some significant questions left to be answered. One of the biggest ones is that if we make measurements of the universe, we see that there's a whole bunch of extra matter that does not fit in with how we understand the rest of the matter that we're used to seeing. And in fact, that's the majority of the matter. So really we understand only, 20% of the matter in the universe. This makes us ask the question, well, okay, there's extra stuff. Are we missing something in our standard model of particle physics? It's been this huge crowning achievement of science, but it misses a few important things. And then a question that probably we won't actually have time to answer because I have far too many slides, addresses the role of the weak nuclear force in chemistry. And we know that most of chemistry is basically just electrostatics, a little bit of magnetic field effects. But in principle, we should also see effects from that weak nuclear force due to the electroweak coupling. How strong is that? So going from the bottom to top here, a key thing about the weak nuclear force is that it does not conserve parity. This was shown, beautifully in the experiments of Madame Wu quite some time ago. I forgot to write down the actual year. But basically, if you have cobalt-60 nuclei polarized in one direction or another, you can think of this in terms of a parity inversion. And if parity were conserved, you would expect that you would still have your beta decay in the same direction. But in fact, it's the opposite way. So in principle, you can actually use weak nuclear decays to determine whether or not the universe is right or left-handed. If I remember right, I think the universe, depending on how you define it, is left-handed in terms of the helicity of how the weak force interacts with things. So within nuclear decays, also in atomic physics, again, Dima Budker has been involved in some of that. And based on what we know, it should also play a role in molecular systems and chemistry. This raises the question of whether it could be related to phenomena like the fact that all of our amino acids have one-handedness and all of the sugars have another-handedness. Is it possible that this is actually a manifestation of the weak nuclear force? And honestly, probably not, but people keep on asking the question, so it's worth answering. Then again, we have dark matter. We know it's there. I can give a much longer talk that goes into all of the exact details of where this comes from. Fritz Zwicky, a very long time ago, measured one galaxy cluster and saw that things weren't rotating quite right. Vera Rubin then went through and made very careful measurements and saw that consistently none of the galaxies were rotating the way you would expect from normal physics. So the easiest answer there is that there's extra matter that we can't see. So this has been observed very well with astronomy. There's better evidence where if this is the bullet cluster where two galaxy clusters collided. In the middle, you can see where it gets, let's see if I can do the pointer. Oh, wait. So there in the middle, colored pink is where we see X-ray emission, which is because all of the normal matter is slamming into other normal matter, getting very hot, emitting X-rays. But if you then look at the gravitational lensing, which tells you where the mass is, it seems to have passed through, being largely unaffected by any collisions. So whereas all of the normal matter got stuck in the middle, the majority of the overall matter passed through. This gives rise to other gravitational lensing effects. Here's dark matter making the universe smile and laugh at us for not understanding what's going on. And if you look at the cosmic microwave background information, you can see that there has to be more matter than what we actually see. So if there's something else going on, that may also imply additional forces. Where this comes into the NMR world, we know that nuclear spins, if it's spin 1/2, we're all very familiar with the nuclear magnetic moment, where our nuclear spins couple to magnetic fields and through precession induce observable magnetization. Of course, for larger spins with the quadrupole moment, you also see coupling to electric field gradients. In principle, one might question whether or not it's possible for nuclear spins to couple to, just a constant electric field. This is a large area of research that I'm not going to go into very much. The tricky thing there is that it violates a couple of discrete symmetries, specifically the combined charge parity symmetry. So you'd expect that there would be some very, very, very small coupling there within the standard model, but it's possible that if there's extra physics, you could find it by looking for that. And then, maybe nuclear spins can couple to dark matter or to gravitational fields or to some other field that I don't know what to call it. So really, it's a question of whether or not we can have, nuclear spin I coupling to something with some coupling constant. We don't really know what that would be, but we can look for some sort of effect. So in any of these measurements, we're looking for a very, very small effect. If it was a big effect, we'd already know about it. There wouldn't be any interest in looking for it. And so as with your normal NMR experiments as well, you have the two challenges, which are signal and noise. So on the noise side, this really comes down to building better detectors, finding a way to get down that noise floor as far as you possibly can. We're not really going to talk about that today because this is a Parahydrogen conference. So we're going to talk much more about how we can boost a signal. That's where Parahydrogen can come in. And the figure of merit that we're interested in is a little bit different from what people often talk about in the hyperpolarization community. People really love to talk about their enhancement. There's a lot of reasons for this. It is actually a rather convenient thing to talk about. Microwaves on, microwaves off. Maybe if you're talking about measuring a very, very mass limited sample, if you're trying to look for, say, fentanyl inside of your heroin, you need to be able to find, maybe in those cases, enhancement is really important. But for us, enhancement doesn't matter. We care about magnetization. We care about absolute signal. So that means we need polarization, we need concentration, we need a large magnetic moment, and in some cases we need volume. If you're talking about, again, I'm working with physicists, so everything is a sphere now. So if you imagine just a spherical polarized volume, if your detector is right there on the surface of that sphere, then the volume, doesn't really matter in the normal sense. Basically the field at the surface of a magnetized sphere is constant. However, there are some cases where if you get a very, very sensitive detector, you can actually get to that sort of next level where volume matters, which is sort of the fundamental limit. Again, it depends on the particular experiment you're looking for, but if you're trying to look for the absence of signal, this becomes especially important because your signal depends on the number of spins. That's the concentration times the volume. But there is an important effect that was actually noticed by Felix Bloch in, basically the original NMR paper, which noted that you should have some uncertainty in the projection of nuclear spins. So there's going to be some random component that's going to be, again, processing about, say, a magnetic field, and this is going to correspond to and be proportional to the square root of the number of spins. You'd still be in pretty good shape. Typical NMR sample pretty easily has 10 to the 22 spins. So if you had an SNR with a 90 pulse of 10 to the 11, you would more likely be limited by the digital resolution of your acquisition system than anything else. But when you stop pulsing and when you start trying to measure zero as well as you can, you have to worry about these kinds of things. And actually, even more important than that, you have this detector back action that's often referred to as radiation damping, which is a little bit unfortunate because if people have read the other papers by David Holt, we should be aware of the fact that there is generally no actual radiation involved in NMR. But again, there is this back action where you induce a current in your detector, which then proceeds to drive nuclear spins further. And actually, if you have just nuclear spin noise, that's just some variation in the magnetic field that is being produced, which gives you a variation in the flux, which then drives a current. That current then feeds back onto your polarized system and actually drives further magnetization into the transverse plane. So, over here on the left, this is some data that we got from Bruker. This is basically a water sample inside of a 600 megahertz, I think it's a warm probe. So it took 5 seconds for us to be able to see a definite signal coming from that spin noise. Then over here, we actually have some data from EPFL where they applied a 90 pulse. So this is the signal you see on top. And then one where they turned up the receiver gain and did not pulse. And you can see that much, much smaller peak there. The problem with the y-axis here is that it was again on Bruker instrumentation, and I have no idea what receiver gain means on a Bruker instrument. So don't worry too much about the details of that, but in general, it's a measurable thing. So in principle, I would talk to you guys about 3 things. We'll see how far I actually get. The first topic is ultralight dark matter. Usually I tend to try to finish up with the dark matter part, but Matt insisted when they invited me to give the talk that he wanted to hear about axions. So we'll start there. Then we'll also talk a little bit about the possibility of other new spin-dependent forces that are beyond the standard model of particle physics. And a topic that we almost certainly won't get to, but maybe I can go through it quickly, is related to these possible weak force effects in chemistry. So molecular parity non-conservation. Wondering to what extent the universe respects this symmetry. So again, always the more fun slide to start with. This is a question of, for most of us, probably one of our favorite techniques, NMR, coupling into, a fun sort of science fiction feeling topic, dark matter. Again, this slide I've already showed you guys. We've seen evidence from galactic rotation curves. We've seen evidence from astronomy in terms of gravitational lensing and X-ray. And when we look at the universe as a whole, there is clear evidence that there is extra material. So we know that there's dark matter. The question is, what is that dark matter actually made of? So we know that it doesn't satisfy any of the basic requirements for what we'd call baryonic matter, stuff that's made of atomic nuclei and electrons. So it's different from us. Otherwise, we'd be able, we would see signals from it. It interacts with gravity. That's how we're able to actually see what's going on. And that's it. There's a huge number of possible candidates. This is why we pay theorists. My favorite ones are the gravitinos and neutralinos and snootrinos, just because they're kind of funny sounding. But the ones that we're going to be really interested in this case are these sort of wavy dark matter candidates. Dark photons, axions, axion-like particles. WIMPs are, of course, have historically been very popular, but people keep on not measuring them, which is good for us. These massive compact objects and black holes are increasingly excluded. So the axion is a new possible fundamental particle that was introduced by Pecci and Quinn some time ago. It's very well theoretically motivated. It actually solves multiple problems. It's also potentially related to the imbalance between matter and antimatter in the universe. The important things are that there's theorists like it. It should have a very high occupation number because it's making up all this dark matter. So it behaves kind of like a classical field. It oscillates just because it has a mass. It's the simplest way to think about it. And it should actually couple to nuclear spins. So that's where we come to the cosmic axion spin precession experiment. Basically what you have, one of the number of possible couplings. The one that we're interested in Mainz is what we call the wind coupling, where we have a gradient of the axion field that couples into our nuclear spins. Again, if you think about that, gradient of a field, remember some quantum mechanics, you think of that actually as a momentum, or the relative velocity between our experiment and this background dark matter field. So you can think of that as the nuclear spin coupling into a velocity. Of course, we all know the Zeeman interaction, where we have this coupling constant gamma, and the vector that we're coupling to, or the pseudo vector we're coupling to, is magnetic field. In the case of the wind, it's basically just a different coupling and a different pseudo magnetic field. So again, what happens is we have a dark matter field, it's oscillating, and if that dark matter frequency is equal to the Larmor frequency of nuclear spins, it will drive spin precession. So we take some hyperpolarized nuclear spins, put them in a tunable magnet, and detect the transverse magnetization. If there is some pseudo-magnetic field that is driving spin precession, we will get precessing magnetization. And if it's big enough, we can measure it. And that's basically the game. So basically, we're using it as a nuclear spin transducer to convert the dark matter field, pseudo-magnetic field, into a real measurable magnetic field. So we have two things we don't know. One of them is the mass of the particle, or the frequency, and the other is the strength of that coupling. You may notice from this axis that we have to, we're trying to cover, a mere 14 orders of magnitude in frequency or mass. And the strength of that coupling is really basically unknown. It's model dependent. There's some possibilities of places to look. So really we don't, it's mysterious. There have been some experimental work that's been done looking for new forces that can also constrain that coupling strength. There are some astronomical observations as well, looking at the cooling of supernovas. If you have this coupling, you should start to see it in other places. But again, it's, astronomical observations are a little bit different from laboratory science. So, in the sort of, lowish field regime, sort of kilohertz to megahertz, we've been building an apparatus that we're calling CASPER-Wind low field. That one uses xenon, so I won't talk about it very much, but I thought I would show some pictures because I think it looks cool inside of this Faraday shielded lab. And, when you start cooling it down, you get some fog. But more what we'll be talking about is actually some zero and ultra low field or very low frequency measurements. Because again, we already have the ZULF NMR apparatus working. So ideally, maybe you can just use it in the meantime as a benchtop dark matter detector. So again, in a typical experiment, as was sort of hinted at by Michael, you start by pre-polarizing in some magnetic field. You transfer down to zero field, you apply a pulse, and you see, heteronuclear magnetization beating back and forth based on the J coupling. This would be a 10 to the 6 enhancement relative to the polarization under the J coupling at zero field. Again, this is why enhancement is sort of funny. However, you can also see a little bit of the possibility of sidebands if you had some sort of additional oscillating field. So if you apply some DC field, you have a very small splitting. So you have a peak of the J coupling, but then you have a Zeeman splitting on top of that. If you have a magnetic field in addition to that, you get sidebands just because you are adjusting the frequency. So collect a bunch of spectra, get Antoine to look very carefully for some sidebands, and then perform exclusions. So we had a little coherent averaging approach. It's really straightforward, but around that time, people were publishing in Science by doing the same kind of thing with diamonds. So we figured we'd make a nice, pretty picture. If you apply the appropriate phase shift that would correspond to your carrier frequency, then you can actually average the sidebands in phase while eliminating the carrier, which is good. This is similar to top spectroscopy that was invented actually in Mainz, just down the street 20 some years ago, or 30 years ago, I don't know, long time ago. And so we were able to show that in principle, we put in a fake axion, which is basically me turning the dial of a frequency source, putting tape over it so that Antoine couldn't see it. And then he was able to find that signal by doing this sort of search. When we did it again without the signal, we were able to put limits. We beat the other experimental limits by a little bit. We have a ways to go for the astronomy, but in the next phase, we should be able to beat it. And that's where parahydrogen comes in as I run out of time.
Yeah, you're well into the question and answer time now. So
all right, I'll go very quick. I'll just bullet points. Give me one more minute. So we get a big enhancement of what we had before, along with Thomas. Ages ago, we showed that we can also do SABRE at 0 field to get a big enhancement. You can do this. We've done this again, nicely to make sure that we get nice long signals. You get very, very nice SABRE-SHEATH sort of build-up curves. These are actually 5 sigma confidence bands. With that, we're able to see that actually one of the major limitations of SABRE-SHEATH is that you have interference between positive and negative polarization. So in principle, you're actually wasting a factor of 3 or so. However, this only works for a few hours, and there's some shifts in the frequency which are problematic for us. So we will be going to much higher pressure, much larger samples, a little bit delayed. The workshop has made this. I've glued some stuff to things. There was a brief attempt to use a vacuum window to look inside. That was a poor choice. That later blew up. Fortunately, nobody was hurt. Very soon, we will be seeing integration of that into another setup where we'll actually be able to have much, much higher sensitivity. And another feature of this is actually that we should be able to build a, I wouldn't call it a razor, but a self-oscillating nuclear spin resonator. So again, as I expected, I probably can't talk about many of these other things, but I'd like to thank all of the people that contributed to this work. There we go. And I am happy to answer any questions.
Thank you so much, John. Yes, a wonderful contribution, thinking about dark matter and magical interactions that we may or may not know about yet, or that we don't know about yet, and that we're trying to find. So that's really kind of amazing. So let me just ask you a couple of brief questions. So there's one question which says, how can you filter out all of the other possible interactions that could perturb the spin as well? Is the shielding good enough?
So, if you'll allow me a brief second. So, one advantage of working at very low fields is that the stability of the field is extremely good. I think our current sources are something like a nanotesla per month sort of stability. But again, that can still be the limitation. So what we can do is we can actually use comagnetometry techniques. A neat trick that we implemented a couple of years ago was to use a CH3. And because those 3 identical protons can add up to give either a total spin of 1/2 or 3/2, we actually have 2 resonances, even just with a single molecular species. And actually, the way that these peaks split as a function of magnetic field is different. It depends differently on the different magnetic moments, and therefore we have a built-in comagnetometer, so we can cancel out any real magnetic field effects and look selectively for exotic pseudo-magnetic field effects.
Okay, yeah, that's beautiful. Thank you